AP Chemistry Unit 9 is actually two mini units, the second law of thermodynamics and electrochemistry. Even though this is the last unit of the course, don't leave this one to chance. It's still a very important unit in the course. Hi there, my name is Jeremy Krug, and this is the place for all things AP Chemistry. And you're about to learn the 10 things you've got to know from Unit 9. If you're new here, welcome to my channel. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe. YouTube tells me that nearly 80% of you haven't subscribed yet, so click that subscribe button and smash that like button if you learned something from this video. And if you're serious about getting that 5 on the AP exam, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, my exclusive tips and tricks for each unit, and 2 full practice exams in the AP Exam Simulator. You can get a free sample today over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 9. Number 1. Entropy is a measure of how well dispersed a sample of matter is. Gases have higher entropy than liquids, and liquids have higher entropy than solids. For systems with only gases, a greater number of molecules will have more entropy than fewer molecules. We use the letter S to represent entropy, which is essentially a measure of how well dispersed a material is, or if you prefer, the amount of disorder in a system. Generally, solids have the least entropy because their particles are not dispersed at all. Liquids have more entropy because particles are more dispersed. Aqueous solutions usually have more entropy than liquids because particles are dispersed throughout a liquid solvent. Gases have the most entropy because particles are dispersed more so than in the other states. We can use this to predict the change in entropy for different reactions. For example, in this reaction, a mixture of solids and gases is reacting to become all solid. Since a gas and solid mixture has more entropy than a completely solid system, entropy is decreasing. In this process, a solid turns into an aqueous state. Since a solid has less entropy than an aqueous mixture, we can predict that entropy will probably be increasing, so delta S will be positive. In this reaction, we have only gases on both sides of the equation, so the tiebreaker is to count how many particles are present on both sides of the reaction. On the reactant side, we see 7 molecules, while the product side has just 4 molecules. 7 to 4 is a decrease in particles, so that implies a decrease in entropy. Number 2. The total entropy change of a reaction can be calculated by taking the sum of the absolute entropies of the products and subtracting the sum of the absolute entropies of the reactants. Let's say we have this chemical reaction. Generally, your textbook or some other reference source will give you the absolute entropies for the substances, like we see in this chart. The absolute entropy of nitrogen gas is 191.5 joules per mole per Kelvin. The entropy of hydrogen gas is 130.6. Since there are 3 moles, we multiply by 3 to get 391.8 joules per mole per Kelvin. The entropy of ammonia, NH3 gas, is 192.5, and since there are 2 moles, we multiply by 2 to get 385. The sum of the reactants is 583.3, and the sum of the products, of course, is 385 joules per mole per Kelvin. To calculate delta S, we take the sum of the products minus the sum of the reactants and find that the overall delta S is negative 198.3 joules per mole per Kelvin. Looking at the reaction itself, we'd expect a negative number since we start with 4 moles of gas and end up with 2. Number 3. Gibbs free energy change is abbreviated as delta G, and it represents the thermodynamic favorability of a process. Processes where delta G are less than 0 are thermodynamically favored, while processes where delta G are greater than 0 are not thermodynamically favored. When we say thermodynamically favored, we're talking about processes that can spontaneously occur at a given set of conditions, as predicted by the Gibbs free energy of that process. While a non-thermodynamically favored process is one that does not spontaneously occur at a given set of conditions as predicted by the Gibbs free energy. As an example, hydrogen burns in oxygen gas to produce water vapor. This is a thermodynamically favored process. Perhaps in the lab, you've seen how hydrogen burns with oxygen quite readily to make water vapor. For all thermodynamically favored processes, delta G will be negative. That means that the reverse process, in which water decomposes to produce hydrogen gas and oxygen gas, would not be thermodynamically favored. That delta G would be positive. Now, that doesn't mean that this reaction could never take place, but it means that a fairly large amount of effort in the form of energy would have to be invested to force the reaction to occur. Number 4, the value of delta G can be determined if we know delta H, temperature in kelvins, and delta S of a reaction. The thermodynamic favorability of a process can be estimated from just the signs of delta H and delta S. Imagine an exothermic reaction with a delta H of negative 196 kilojoules per mole. The same reaction has a delta S of negative 206 joules per mole per Kelvin. Determine the value of delta G for this reaction at 298 kelvins. We use the equation delta G equals delta H minus T times delta S. We're solving for delta G. The delta H is given to us as negative 196 kilojoules per mole. I'll convert this to joules. The temperature is 298 kelvins, and the delta S is negative 206 joules per mole per Kelvin. We do some math and find that delta G equals negative 135 kilojoules per mole. The negative sign tells us this reaction is thermodynamically favored. Now, we can use the signs of delta H and delta S to predict the thermodynamic favorability of a process. If a reaction is exothermic, its delta H is negative, and if its entropy is increasing, delta S is positive, the process will be thermodynamically favored at all temperatures. But if you have the opposite, an endothermic reaction, and delta S is negative, then that process will never be thermodynamically favored. If both delta H and delta S are positive, the process will be favored only at relatively high temperatures. On the other hand, if both of them are negative, the process will be favored only at relatively low temperatures. In an earlier problem, we looked at a reaction that had a negative delta H and a negative delta S. We've already calculated the numerical value of delta G, but just by looking at the signs for these two quantities, they're both negative. So the reaction will be favored only at relatively low temperatures. Number 5. Sometimes reactions that are thermodynamically favored don't actually seem to be occurring. This is because they're under kinetic or thermodynamic control, often due to a very high activation energy. Let's take this reaction in which liquid acetic acid decomposes to form diamonds and liquid water. This sounds like a very interesting reaction, and since delta G is negative, this is a thermodynamically favored process. But if we take a bottle of acetic acid, which you can find in most chemistry laboratories, do you think you'll see diamonds forming spontaneously out of that acid? Well, of course not. And that's because the reaction is under what's called thermodynamic control. The activation energy for this process is extremely high, so if it occurs at all, it's going to happen extremely slowly. In fact, we can say with certainty that this reaction does not happen because its activation energy is just so ridiculously high. And to clarify, the reaction is not at equilibrium. It just means that the kinetics of this reaction prevent it from happening even though it is technically thermodynamically favored. Number 6. The thermodynamic favorability of a reaction, delta G, is very closely related to its equilibrium constant, K. Thermodynamically favored processes will have an equilibrium constant much greater than 1, while non-thermodynamically favored processes will have an equilibrium constant much less than 1. Now, we can relate delta G to an equilibrium constant with this equation. Delta G is the change in Gibbs free energy. R is the universal gas constant equal to 8.314 joules per mole per Kelvin. T is the temperature in kelvins, and we have the natural log of the equilibrium constant. So if we have this problem where we have a delta G of negative 254 kilojoules per mole, and we're asked to determine the equilibrium constant K for this reaction at 298 kelvins, well, we just plug and chug into the equation. Delta G is negative 257,000 joules per mole. R is the universal gas constant of 8.314. The temperature is 298 kelvins, and we're solving for the equilibrium constant. We do some math and find that the natural log of K is 104. If we take the anti-natural log of that, we find that the equilibrium constant is about 1 times 10 to the 45th, which is a huge number. And since that's a very large equilibrium constant, much, much larger than 1, the reaction is absolutely thermodynamically favored. And that was confirmed by the delta G given in the question. On the other hand, if we have a very small equilibrium constant, much, much less than 1, that process will not be thermodynamically favored, and we'd have a positive value for delta G. Number 7. Galvanic cells, such as batteries, are thermodynamically favored redox reactions in which electrons pass through a wire from an anode to a cathode. Oxidation takes place at the anode, and reduction takes place at the cathode. In this sample galvanic cell, we have 2 metal electrodes and a potential difference, or voltage, of 0.48 volts. And the electrons are passing through the wire from the tin electrode to the copper electrode. In any galvanic cell, electrons flow through the wire from the anode to the cathode. So that means tin is the anode and copper is the cathode. Oxidation always occurs at the anode, while reduction always occurs at the cathode. So that means that tin metal is being oxidized into tin 2+ ions, and copper 2+ ions are being reduced into copper metal. Whenever we have cells with 2 metallic electrodes like this one, the anode decreases in mass while the cathode increases in mass. So as this cell runs, you'd see the tin electrode decreasing in mass while the copper metal would be increasing in mass. At the salt bridge, anions will be flowing toward the anode and cations will be flowing toward the cathode. Number 8. The voltage of a galvanic cell can be calculated using the 2 reduction potentials of the half reactions. The potentials can be subtracted to determine the overall potential, or voltage, and the identity of the cathode and anode. Galvanic cells are always thermodynamically favored, while electrolytic cells are never favored. Let's say we have a galvanic cell where on one side we have aluminum metal sticking into a solution containing aluminum 3+ ions, and on the other side we have a piece of iron metal sticking into a solution containing iron 2+ ions. These are the standard reduction potentials and half reactions for those processes. We can look these up in a textbook or they'll be given to us on a test. We use this equation. E cell equals E cathode minus E anode to determine the overall cell potential. Remember that for any galvanic cell, the voltage has to be positive. So we subtract those 2 values in both directions and see which one gives us a positive number. Well, the first one gives us a negative number. It's the second one that's positive. So the overall voltage of the cell is 1.22 volts. The value in the first position represents the cathode, so iron is the cathode. The value in the second position is the anode, so aluminum represents the anode. When we add these half reactions, the cathode half reaction is written as it's given. We always flip the anode half reaction. Since aluminum is the anode, we flip that half reaction and write it as an oxidation. When adding these together to get the overall equation, we need to make sure that the electrons cancel out and disappear when they're added together. So to make that happen, half reaction number 1 needs to be multiplied by 3, and half reaction number 2 needs to be multiplied by 2. Then 6 electrons will cancel, and we get our overall balanced equation. Number 9. The Nernst equation tells us that when Q, the reaction quotient, increases for an electrochemical cell, its potential decreases. When Q decreases, the cell potential increases. As a galvanic cell runs, its Q value increases, its E cell decreases, and eventually reaches equilibrium, where E cell equals 0 volts. The Nernst equation looks like this. Although you'll likely never have to numerically solve anything with this equation, it's important to know that when the reaction quotient for the cell increases, the voltage decreases. Likewise, when Q decreases, the voltage increases. So if we have this reaction and we use 1 molar iron ions, but we use 1.2 molar aluminum ions, how will this affect the voltage compared to standard conditions? We can calculate Q by plugging the molarities into the expression products over reactants raised to the power of the coefficients, and we find the value for Q equal to 1.73. Since that's greater than 1, E cell will be less than it would be at standard conditions. Now, to generalize this, if we increase the products or decrease the reactants, mathematically the value of Q will be greater. And remember, when Q increases, the voltage decreases. The opposite is also true. If we decrease the amount of product concentration or increase the reactant concentration, the value of Q gets smaller. And when Q gets smaller, the voltage gets larger. And eventually, the galvanic cell will reach equilibrium where the voltage will be 0 volts. And that's what most of us would call a dead battery. Number 10. Faraday's law tells us that the electrical current in amperes is equal to the quantity of charge transferred in coulombs divided by the time in seconds. Coulombs can be converted to a quantity of an element using Faraday's constant and a balanced half reaction. Faraday's law looks like this. I, which is the current in amperes, equals Q, the quantity of electric charge in coulombs, divided by the time in seconds. If we know any two of these values, we can solve for the third. Let's try an example. A chemist passes a current of electricity through a solution of gold 3 plus ions in order to plate gold metal onto a surface. If the chemist passes a 30 amp current through the solution, how long will it take to plate 25 grams of gold metal onto the surface? The first step is to convert from grams of gold to coulombs by stoichiometry. In this process, we're starting with gold 3 plus ions and we're trying to convert it to gold metal. So it requires 3 electrons for that to happen. This is our balanced half reaction. We start with 25 grams of gold and we're trying to find how many coulombs it takes to make that happen. Just like any stoichiometry problem, step 1 is to convert to moles. That means grams on bottom, 1 mole on top. The periodic table tells us there are 196.97 grams in a mole of gold, and grams are out. Step 2 is the mole ratio. Gold goes on the bottom, electrons go on the top. We can look at the balanced half reaction and see that it takes 3 electrons to make 1 gold atom. Gold is out, top and bottom. Step 3 is to convert to our final unit, which is coulombs. We put moles of electrons on the bottom and coulombs on top. Faraday's constant tells us that there are 96,485 coulombs in 1 mole of electrons. We cancel moles and electrons, and now we do our math and find that this requires 36,738 coulombs. Now we can calculate the amount of time required for the process. We use Faraday's law for this. I is our current, which is 30 amps. Charge was just calculated, which is 36,738 coulombs. And we're solving for time. We solve and find that it takes about 1,220 seconds for this to happen, which is about 20 minutes and 20 seconds. And that's it. Those are the 10 most important things you've got to know from Unit 9. If you're serious about upping your game for the AP exam, my Ultimate Exam Slayer for AP Chem has 60 AP-style multiple choice questions for Unit 9 and for every one of the units in the course. That's way more than AP Classroom. You can get my Exam Slayer along with the Ultimate Review Packet, and you'll have everything you need to succeed in AP Chem. So go check it out over at ultimatereviewpacket.com. Hey, thanks for watching, thanks even more for subscribing, and I'll see you soon.